Hear me? Hello. Okay. Can everybody hear me okay? All right, cool. Hi, everybody. My name is Edward Chen. I'm a software engineer on the ORT Mobile team. Today, I'll be talking about ONNX Runtime on the Edge. So, quick overview of ORT. We've already gotten some good introductions earlier. Then I'll talk about on-device training with ORT. We'll walk through an example showing on-device training. And finally, we'll go over some relevant ORT mobile features. So ONNX Runtime, the main feature of it is that it runs ONNX models. ONNX models being that of an open source ONNX format. So ONNX Runtime is a high performance implementation of the ONNX spec. It supports both inference and training workloads. As mentioned before, there's support for hardware acceleration on many different platforms via these execution providers. There's that CPU EP, which is kind of the fallback implementation. It's also high for performance. And CUDA for NVIDIA GPUs, Kernel for Apple platforms, and an API for Android. And there's quite a few others. ORT runs on multiple platforms, these desktop platforms as well as mobile ones, and is usable from many languages. So why do on-device training? Why train the model directly on the device? It has some significant benefits. If we don't have to make a request to the cloud, then we have better latency and availability. And importantly, the data stays on the device, so there aren't any privacy concerns associated with sending the data somewhere else. Two main scenarios supported by ORT are personalized learning and federated learning. For personalized learning, we are training the model on the device to get more personalized results. So in this picture here, everything will happen on our device. We can start with a pre-trained model of some sort, then train it with more data that's gathered from the device. Do this training loop until we've sufficiently trained it, and then export a model for inferencing that has been optimized, and then run some predictions on that to get more personalized results. Some example applications are image and audio classification and text prediction. Say, like a user's, a particular person's voice could be trained to be recognized. The other main scenario is federated learning, in which we update a global model, but also keep the data on the device. So in this picture, it's divided into two parts. The one on the top is on the device, and that's where the training with the data happens. And separately on the bottom, on the server, that's where the global model state is maintained. So from the device, it will send like the deltas in the model that it has computed from training with the data back to the server, and those get aggregated and used to update the global model state. Some applications are medical research and advertising. So some benefits of training on-device training with ORT include use of a memory and performance efficient trainer. So on these mobile edge devices, often it's more resource constrained, so we can still do training there. There's a simple and consistent API for on-device training that's supported on these languages and these platforms listed here. Android and iOS are relevant here today. And finally, we can easily move from doing our training to exporting an optimized inference model and running inference with the same binaries and the same packages. I'll go over the general workflow for doing on-device training now. So first, we start with our ONNX model. This can be exported from a variety of different source frameworks, like PyTorch or TensorFlow. This will be a forward model, which one can use for inferencing. Now that we have an ONNX model, we can use some artifact generation scripts to generate our training artifacts. And still offline, we can do some validation of our training recipe to make sure that it works as we expect. And then once we're happy with that, we can move on to the device, taking our same training artifacts and using one of the mobile packages with the training APIs included. We can write some code on an app and do training there. This is possibly in some more mobile relevant languages like Java or Kotlin or Objective-C. And then once we've trained enough on the device, we have some options. We can save a checkpoint to be used in further training later. We can export the model for inference and run predictions with it, as we saw in like the personalized learning scenario. We can extract the weights and use that information to send some updates to a global model, as in the federated learning scenario. Yeah. So now let's take a look at an example. In this example, we'll start with an image classification model, and we'll select 4 new categories that we want to classify images into, and we'll train this updated classifier layer on some our own image data. So as we saw in the workflow, we have a couple stages. Offline first, we'll prepare the training artifacts and then validate the recipe. Then we'll move on to a device, in this case Android, and show how to train and eventually inference. So I've pre-recorded some videos to show this. Let's get them to play.
Let's go over how to get our model and effects. So for this example, we'll be using the PyTorch MobileNet v2 model that has been pre-trained on the ImageNet dataset, which has 1,000 categories. In this example, we'll be classifying into 4 categories, so we want to change our last classifier layer to have 4 outputs instead. Then we can go and export that to ONNX. Let's start that. It's going to take a little while to run. Okay, now we have our ONNX model. Let's take a look at it. So here's our MobileNet ONNX model. Note that it is a forward model that one could use for inference. We had updated that classifier to have 4 categories instead, so we can see that our gem output here matches that with the 4. And let's also note these 2 parameters here, classifier 1 weight, classifier 1 bias. These are the parameters that we wish to train. Okay, now let's produce our training artifacts. Those consist of the training, eval, and optimizer ONNX models, as well as a checkpoint file that contains model parameters. We can use this ONNX Runtime Training Python utility to generate the artifacts. Recall those 2 parameters that we looked at in the model, those are the ones that we want to train. So we set requires grad to them and the frozen params to all the other parameters. And then we can set a loss type, an optimizer type called generate artifacts. So here are training artifacts. Let's take a look at this training model. It has a lot more stuff, but the interesting part is around those two parameters that we wanted to train: classifier, weight, and bias. So we can see, starting from the loss function, there's the gradient computation that goes back for just these two parameters, and we end up with the gradient values as outputs. Right, now that we have our training artifacts, let's go and do something with them.
Okay, so next we'll show how to validate the training recipe.
Let's validate our training recipe with the ORT training Python API. This will be done offline. We will be using an animal image dataset to classify animals into 4 categories: dog, cat, elephant, and cow. First, we'll collect the image file paths. The MobileNet v2 model expects the inputs to be in a certain format, so we'll need to pre-process the images. In particular, the images need to be 224 by 224 pixels, and each pixel value must be normalized by subtracting a mean and dividing by a standard deviation that is expected by the model. Let's define this pre-processing function. Let's also define some variables that will be used by the training loop. The number of images we have per animal is 20, and we will be going through the entire training data 5 times. Now let's take a look at the training loop. I'll start running this first as it takes a while. The ORT training Python API provides 3 classes that we will interact with. The checkpoint state contains the model parameters. The training module will execute the training and eval graphs, and the optimizer will update the model parameters in the direction of the computed gradients. First, we'll instantiate these 3 objects with the training artifacts that we produced previously. And this is the actual training loop. It will go over the entire training data in each epoch. And in the inner loop here, we will take a batch of 1 image from each animal type and run that with the training model. This will result in some computed gradients. And then this optimizer step call will update the model parameters by taking a step in the direction of those gradients. And then we'll reset those gradients so that in the next iteration, the new gradients can be computed. This is finished running, and we can see that the loss has decreased. Now we can export the model for inference and try to run a prediction on it to see how well it does. We'll be using an image that hasn't been seen yet. So given this nice picture of a dog, the model is 68% confident that it is a dog.
Okay, now we can look at how to train on an Android app.
Let's take a look at an Android app that does training. So here, this ORT personalized app that's running in the emulator. We've copied over our training artifacts that we've generated previously, as well as the training image data set with all those animal pictures. This app depends on the ONNX Runtime Training Android package, which provides the Java bindings. And this app is written in Kotlin, which is interoperable with Java. So notice here that this app provides the capability of specifying their own custom classes, as well as the training images for those. But for the purposes of this demonstration, we'll just keep using the animals categories as we did before. I've set some breakpoints in this ORT trainer class. This class contains the ORT API usage. So let's hit this training button and see what happens. Okay, we've arrived in this perform training function. The Java API looks a little different from the Python API. So we have this ORT environment, which is required for other usages of the ORT API, and a training session with which we can do our training, and a regular session, which we will use to perform inference. Okay. In the constructor, after hitting the environment instance, we will create a training session using these paths to the checkpoint and the models, which are just from the training artifacts. In perform training, this happens to be inside the inner loop of the training loop. We will see this these calls to the training session, train step, optimizer step, and reset grad. Now these correspond to the Python training inner loop calls. This train step will run the training model and compute the gradients. Optimizer step will apply the weight updates to the parameters based on those gradients. And reset grad will reset those gradients for the next iteration. Let's step out of this inner loop function and take a look at the rest of the loop. I will resume execution after disabling this breakpoint. It'll take a little while to run. So let's examine the rest of the training loop. It looks similar. We have a outer loop that goes over the epochs in which we step through all of the training data, and inside we will handle the training images in batches. So as we saw in the Python code, we need to do some pre-processing of the image. This is similar. Process bitmap will do the cropping and resizing to what MobileNet requires, which is that 224 by 224 resolution. And process image will do that pixel normalization that was required. Back to the training loop. After we've done that pre-processing, we will get our image data and the corresponding labels and pass those inputs to perform training. There's also some updates to the UI to indicate the progress. And we see this training complete message now. So our training has been completed. Now let's try an inference. I happen to have a picture of a cat saved on this emulator. We'll go with that. Now we've arrived in perform inference, back in ORT trainer. So as we've seen in Python, we will export the model for inference. This will write inference model.onnx file. And then with that, we will create a ORT session and use that to run the inference. The session.run call with the image data will return us an output, which should indicate the prediction. So let's see what happens. As we suspected, this guy is a cat.
Okay. So this example is available on GitHub if you want to take a closer look at it. Use the Python API and the Java API, the on-device training APIs. So the references to those are there. Now let's talk a little bit about some ORT Mobile features. ORT Mobile is a variant of ORT that minimizes the binary size for such mobile and edge scenarios. Importantly, it uses the same code base as ORT, but it provides the option to do these builds which can exclude certain functionality in order to reduce binary size. And the runtime API usage remains the same. There's two primary approaches to reducing binary size. We can have a reduced operator kernel build in which we only include the operators that are required to run a model. There's an option to further just reduce it to include the implementations of those operators for specific types that are used by the model. And we can also create a minimal build in which certain ORT core code is excluded, which reduces binary size. One consequence of this is that the ONNX file loading, that is no longer supported to remove some of the dependencies. So there's a custom ORT format model that is required in a minimal build. One thing to note is that minimal builds don't support this training export for inferencing API that we saw used in the personalized learning example. So a reduced operator kernel build requires the specification of the operator kernels to include, and that's through a configuration file. It can be generated by a script, which we'll look at a little later. And it can also be manually edited or written by hand, as it's just a text file. An example config file line is like this. You can see we specify the domain, offset, and the ops that we want from those. There can be multiple lines if you have multiple domains. And as mentioned, we can also be more granular about what we want to support by specifying the types for the particular operator kernels. The script can also detect this from the models, or you can specify a globally allowed types list that specifies what types should be supported by all operators. And this kind of type reduction can also significantly reduce the kernel binary size. There's some more information about this at that link there. Now, for a minimal build, as mentioned, we need to use this ORT format model that is created from a source ONNX model, and we have a Python script that does that conversion. It also generates those config files that mentioned in that previous slide for the reduced operator types. During conversion, some things happen. Notably, we apply some ONNX runtime optimizations to the graph, like constant folding and other basic level optimizations, which don't change the semantics of the ONNX ops. And if such an optimization has already been applied and its effects are saved in the ORT format model, then in a minimal build, we can exclude the implementation of the optimizer, which can save a significant binary size. And also in the ORT format model, we also save op schema type constraint info. And this enables kernel assignment to happen in a minimal build without a dependency on the ONNX schema, which also has significant size savings. The ORT format model uses flat buffers, so it is specified with a flat buffer schema. And there's more information about it at this link. So how you might use these features is, first you would probably want to start with a full build of ORT. It's the path of least resistance. There are already pre-built packages for Android and iOS, which should be fairly easy to consume. These full build packages have all the features enabled and all of the operators available. So it should be easiest to get something up and running with that. And at that point, if everything looks good, then you're good. Otherwise, if the binary size is too large, you might consider a custom ORT build. And you can either reduce the operator kernel implementations or try a minimal build and convert your models to ORT format. These two approaches can be combined. And there's some more documentation about how to do a custom build there. And finally, I'd like to just mention that in ORT 1.17, there's our new on-device training web APIs available in JavaScript through this ONNX Runtime Web package. And here's an example showing how to use it at this link. And yeah, that is all I had. Any questions?